said chapter 23?
Correct. Yes.
And you said number 2?
Yes.
So we have two charges, Q1, Q2, are placed symmetrically along the x-axis at plus and minus 3. So that's the x-axis. That's the y-axis. So there's one over here at 3 centimeters, which is 0.03 meters. And the other one here, 0.03 meters. So there's one charge here. Another one here. And 2 microcoulombs, oh, they're both 2 microcoulombs, right?
Mm-hmm.
So this is 2 microcoulombs and 2 microcoulombs, right? Consider another charge of 4 microcoulombs with mass 10 milligrams moving along the y-axis. If Q3 starts from rest at 2 meters, so this is Q3, and this is 2 meters, right?
Centimeters.
Centimeters. Thank you. And the charge is positive, right?
Mm-hmm.
So they repel one another. And this charge is it 4 microcoulombs?
Yeah.
Okay, so this one is 4 microcoulombs. Let's call this Q3. And I can call either one Q1 and Q2, it doesn't matter. And they're positive, positive, and this is positive, right? So the initial position of this charge is there. And we know that the initial speed is 0 because it says that it is released from rest, right? And we're given the mass of it also, right? Was it 10 milligrams?
Yeah.
So it'll be 0.01 kilograms. And it is released from rest. So first of all, which way should it go? Independent of what it says over there. Because this one is pushing it this way. This charge on the left is pushing it that way. This other charge exerts a force of the same magnitude, but in this direction, those two x components of forces are going to cancel. The only force is going to be along the y-axis, so it's going to move along the y-axis, right? So what is the speed when it gets to 4 centimeters? So later on, it's going to go this way, right? And we want to know when it gets there, what the speed is going to be, right? When all of this is 0.04 meters, right? So this calls for what? What should I use to solve this problem?
Work energy theorem?
The work energy theorem, conservation of energy. The only force is electrical energy, which is a conservative force. So I can just equate the kinetic plus potential energy at the beginning to the kinetic and potential energy at the end. So I can say, from conservation of energy, I can say, the initial energy equals the final energy. Now, in physics 185, you call this the initial mechanical energy because it was kinetic plus gravitational potential energy plus elastic potential energy. Well, this energy is kinetic energy plus electrical potential energy, and that's not mechanical. So I'll just call it energy. All right, so the initial energy will be its initial kinetic energy 1/2 m times v initial squared plus the initial electrical potential energy. What will be the initial potential energy? It will be, what should I write down? Which charge should I write down here? Q1, Q2, or Q3?
Q3.
Q3 multiplied by what? By what should I multiply by?
K.
What?
K?
What's the formula for potential energy?
Isn't it KQ over R?
KQ over R is electric potential, not potential energy.
Oh.
So what's the formula for electrical potential energy? Q times the potential. So if I want the potential energy of this charge, it's going to be that charge multiplied by the potential there, which is the external potential at that point, right? So this is PV, right? But who's going to create the potential at this location?
Q1 and Q2.
Not Q3, because then I would say K Q3 over 0, which is undefined. So the potential at that point is created by the other two charges. So I'll just call it V, like initial. That's the electrical potential, not potential energy. This V is not potential energy. When I multiply by the charge, then it is the potential energy. But this is the electric potential generated at the location, at the initial position of Q3, generated by the other two charges. And then what is the energy of the charged particle of Q3 when it gets here? It will be its kinetic energy there. I'm looking for that speed, right? And now I want its electrical potential energy when it gets here. So what would its electrical potential energy be? The charge there, which is Q3 times the potential there generated by the other two charges, right? Which I'm going to call V final. Notice this V is lowercase v for speed, capital V is for potential in volts, right? So I use a capital V for electric potential, lowercase v for speed. So what would this be? This would be, first of all, this is 0, correct? We're told that the initial speed is 0, right? Yes. So what should I write down for Q3? Q3 is 4 microcoulombs, so it'll be 4 times 10 to the minus 6 coulombs, right? That's Q3. What should I write down for V naught, or V initial? What is the electric potential at that point where Q3 is initially?
KQ1 over R plus KQ2 over R.
So it'll be the potential there due to Q1, yes, KQ1 over R1 plus the potential there due to Q2. So it's KQ1 over R1, so it'll be K 9 times 10 to the 9th. Q1 is 2 times 10 to the minus 6. That's microcoulombs divided by which R? So now I need this R, right? And that's the square root of this square plus that square, right? Plus, that's the potential at this point due to this charge. Now, what is the potential at that point due to the other charge? K Q2 over R2, which is going to turn out to be the same thing, right? 9 from symmetry. It's the same charge, and it's the same distance. And that equals the final kinetic energy, which is 1/2. The mass is 0.01 kilograms times the speed squared, right? Plus, now what is the final potential energy, electrical potential energy of this charge? it's going to be the Q3 when it gets there, which is 4 microcoulombs, right? Times the potential, electric potential there due to the 2 charges, right? Due to these 2 charges. So what is that going to be? Can you see right away what this distance is? What is this distance here, from here to there? That's 3, 4, that should be a 5, right? 5 centimeters, so this distance should be 0.05 meters. So of course that's a 3, 4, 5 triangle. So the potential there is going to be, due to Q1, it's K, which is 9 times 10 to the 9th, times Q1, which is 2 microcoulombs, divided by that distance, which is, in that case, 0.05, right? Plus the potential there due to the other charge, right? Both Q1 and Q2 are producing a potential everywhere, right? And depending on where this charge is, that's going to have potential energy equal to that charge multiplied by the potential at the location where it's at, generated by the other charges. So this would be 9 times 10 to the 9th, 2 times 10 to the minus 6, divided by 0.05. Or you can just multiply by 2 that expression. So you use your calculator, and your stuff will be fine. Yes? Questions? Questions? Yes?
Professor, in the exam, can we just like write down the answer will be that after we have that?
If you write all of this and then you write down the answer, then yeah, that's fine. What I suggest is that you do not go from here to the number.
Oh, I don't
Because
know.
if it's wrong, I don't know what you did, and then you get no points. Whereas if I see that this is written correctly, then I'll just assume that your wrong answer is because you used your calculator incorrectly. And then that's just 1 or 2 points as opposed to all of the points. Yes? So show what numbers you plugged in, and then I'll see if, maybe your answer is, if that's correct, then the only explanation for the wrong answer is you made a calculator mistake, right? But if I don't see this, but I see this, and then I see a number, then it may be that you didn't make a calculator mistake. It may be that you wrote down the wrong potential over here. You didn't write down the correct charge over there. So, so just so that, because maybe you did the correct thing, but then if you don't show me, I don't know what you were thinking. Right? Also, if you write this and magically you get the right answer, I could also assume that you copied from someone, which is not what you want, right? So, and I'm not saying you did, but what happened all of a sudden this person had the answer, so how did they do that, right? And of course you might have done it in your head, and that's okay, but I need to see what you were thinking, what you were doing, so that, okay, if I see this and then I see that and then I see the right answer, then I know you know how to do the problem. It's not an issue, right? But I see this and then I see the correct answer and I don't know what numbers you plugged into what, and then I begin to wonder, did they cheat? There's so much cheating that goes on that, unfortunately, I stop and I say, well, did they copy the answer from someone else? So show your work, and then it's like, other questions?
Could we take a look at chapter 21 problem? It's 104 from the homework.
104? So from the textbook?
Yeah.
Okay. So this is the disk. It looks to me like this is the disk problem, except that instead of I can see that this is the disk problem, except that instead of integrating, starting with the ring with r equals 0 all the way up to r equals capital R, you integrate from, I guess, R1 to R2, right? That would be the only difference. I mean, with that, imagine if this didn't have a hole in there, then whatever we did with the electric field over here is going to be through all of this charge, and that's the problem that we did. But the only difference between this problem with a hole in there, like a washer type of thing, and the disk filled in, right, is it's by limits of integrations for this R. And if you have this filled in, then you fill this with rings, starting with a ring of radius 0, all the way up to radius, I tend to call it A. But in this case, if this is A and that's B, then you integrate from A to B, or from R1 to R2, depending on what they give you, right? So this part of the problem is just that, right? Well, I just said over here, proceed as in example 2111, which is the one where you have the whole disk, right? And just integrate from R1 to R2, as opposed to from 0 to the radius of the thing. That's the only difference, right? So then you do that, and you get something that looks like this, right? The next question here is, what's the total, let me, it looks like what's the total charge in the ring, in that washer? Do you know how to do this one?
Yes, I was curious though, the way I did it, I expanded out the charge over area, and maybe that's what I was doing.
So there are two ways to answer that question. There's a quick and a longer way. Which one do you want first?
Go the longer way.
The longer one? Okay, so then you have, what you have is this. You have something like this, and like that. And the radius of this is R1, the radius of this is R2. And this is what the charge is. And the charge per unit area is sigma. And what you want to know is, what is this charge, right? Yes. So what I'm going to do is, I am going to choose a ring of radius R and thickness dr. You know, an infinitesimal thickness dr. I'm drawing it kind of big over here, but it's supposed to be infinitesimally thin, right? So this thickness is the R. Now, what is the charge in that ring? if the charge per unit area is sigma? How much charge is in this ring of radius r and thickness dr?
Sigma pi r squared? Or sigma pi r squared?
No, because if you see pi r squared is all of this area. No, I just want it in this thin piece. I don't want there's no charge over here, first of all. This is a hole. So I cannot do it by pi r squared, no. Or give me an expression and then we'll work out the expression. So how would you start?
Sigma RDR.
So what is it?
2 pi r dr?
But what is that? What is that? What does 2 pi r dr represent?
The length times.
No, that's it. It's the area of the strip. So how is the area, suppose the area of this strip is dA. How is that area related to this charge? Let's do that first, and then let's deal with the area, and then let's do the rest. But the very first step is, how much charge is in that ring? It's what?
Charge over area.
So charge over area, that's the charge per unit area, that's sigma. What's that? So it's the charge per unit area, that's just the charge in a unit of area times that area. That's the very first step. It's sigma dA. Yes? The charge in that area is the charge in a unit of area, which is sigma, times that area, dA. Now let's deal with that area. What is that area? This is sigma, it's constant, but what is this area? What is the area of this ring of radius r and thickness dr? Well,
That's 2 pi r dr.
that's the 2 pi r. That's because this 2 pi r is the circumference. That 2 pi r is this. See, that 2 pi r is just the circumference of the circle, right? And if you multiply that length by the width, you get the area. So now this goes in here. So this would be sigma times 2 pi r dr. That's the charge in that strip that's, well, the shape of a ring. Right? So, if you know the charge in that strip, how do you get the charge from here to here in all of this? How do you get all of that charge from that? What is that? What do you do? In other words, you calculate the area in that strip, and not the area, the charge in that strip, which is this, and you add it to the charge in the next strip, and then you add it to the charge in the next strip, and you add it to the charge in the next strip, and, well, you add the charge in all of those strips, starting from here and ending over there. And that sum is an integral. And, from where to where you do that sum, that determines the limits of your integral. No? So, the total charge Q is going to be the charge in that dq, it's the charge in green, and then I have to add the charge in all of those rings. of thickness is dr. And that sum is what this does. So the total charge is the sum of all the charges in those strips. But I have to be careful with my limits of integration, right? So it's only from R1 to R2 that I'm going to. So then I take that expression, and that's just sigma 2 pi r dr, right? And then all of these are constants, right? I pull those, and I integrate from R1 to R2. So this is sigma 2 pi integral of r dr from R1 to R2. So this is sigma times 2 pi, and then that's going to be r squared over 2 from R1 to R2. This will cancel that. And this is just going to give me sigma times pi R2 squared minus pi R1 squared. I can write it like that. No or yes? Now, what's the quick way? What's the quick way? The quick way is this. What is the charge? What is the charge? Let me consider the ring of radius R2. And it's got sigma in there. Suppose it's completely filled. What's all that charge in there? And what would that be in terms of those parameters?
Sigma pi r squared.
Sigma, pi, which are?
R2 squared.
Now, what's the charge in this ring of radius R1 with the same charge per area sigma? What's the charge in that?
Sigma pi r1 squared.
So the charge in this is going to be sigma pi r2 squared, and the charge in this is going to be sigma pi r1 squared. I can think of this, right, as being only here. And what do I need to do to just get the charge between them? I need to get rid of this charge, right? So I gotta take this and I gotta subtract that. And that's what this is. Do you see that? That's the quick way. The longer way would be doing it like this, formally like this. Right? I mean, if I want to know what is the area of this wall over here, but not including the board, I can do that by calculating the area of the whole wall, including the area of the board, right? And then I calculate the area of the board, and I subtract the area of the board from the area of the whole wall. That's just going to give me the area of what's around the board. That's exactly the same as this problem. I don't know if there was another part to it. So there's another part to it. There's another part to this problem. I guess, I mean, I don't have the book, so I haven't read the question, but by what I wrote over here, I can sort of figure out what the question was. So for points sufficiently close to the origin, so imagine you have this washer type of thing, right? like a washer, right? And I guess in the problem, there's a, it goes to radius R1 and then R2, right? And then you got a hole in, right? Like a washer type of thing. And then in the problem, you're asked to calculate the electric field somewhere on the axis, right? So X is from the center of this washer, along this axis, perpendicular to the plane of the washer, right? Now it says, what if you calculate the electric field very, very, very close to it? But not at the center, just close. So close that that X, the distance from the washer to the center, is very small compared to R1, the radius, and R2. So what would happen if that's the case? So the expression for the electric field is this. So we have this expression, this mathematical expression. The electric field is, this means in the positive x direction, right? And then sigma over 2 epsilon naught. And then this is x over r1 squared plus x squared square root. Wait. Okay. Minus x over the square root of this. Right? That's the expression, right? For the electric field. And we want to consider, what if x is much less than R1? If it is much less than R1, it's definitely going to be much less than R2 because R2 is greater than R1. Right? Right? I mean, you have this, right? This is R1 and this is R2. So, if you are off from the center, a little bit off, a distance x, if that distance is small compared to this radius, it's definitely going to be small compared to this radius, which is bigger than that other one, right? So it will be, if it is less than that, obviously x is also going to be much less than R2 because R1 is less than R2. So what if we have that, right? So at first you might say, well then, x is 0. But if I put 0 here, this is not going to be 0 in the denominator. This is 0 there, but then you have an R1 square root of that is R1, so this will go as x over this, so that's going to make it 0, and that's going to make it 0, so the electric field is going to be 0. Well, at the center is going to be 0. But off the center a little bit, it's going to be, well, close to 0, but it's not going to be equal to 0. And that's the question. What if x is not equal to 0, but yet is small compared to this radius and this other radius? Right? So what do we do with this? And this expression, right? So just consider one of them. And you do what's called an expansion. And you pick up the first term that's not going to give you 0 for an answer. Well, the first term in the expansion is that this is going to go to 0, but we don't want that. And if it goes to 1, then 1 minus 1 is 0, so you get a 0 answer. So we want the first non-zero term. Well, the first term that's not going to give you 0. So how do we handle this guy over here, right? So we have this. We have x over the square root of R1 plus squared plus x squared, right? So I want 1 plus a small number. So that means I gotta factor out R1. So this would be x over the square root of R1 squared, and then that's 1 plus x squared over R1 squared, correct? Agree? If I take this and I multiply by that, I'm gonna get this, right? Yes?
Yes.
And what is the square root of R1 squared? R1. So this is going to be x over R1, and then I have 1 plus x squared over R1 squared to the 1/2, right? Instead of using the square root, I'm going to use that just raised to the 1/2 power, right? Now, this quantity here is very small. Right? Because x is much smaller than R1. And in fact, that's ridiculously small. And then I square it, it makes it even smaller, right? So at first sight, you might want to just, set it equal to 0. But then you'll end up getting 0. Because then x is going to go to 0. Then you just get that the electric field is 0, but that's really going to be at the center. But we want to be a little bit off the center, right? With the first order correction. So how do I deal with that? So what I'm going to do is I'm going to bring this from the denominator to the numerator by writing it like this. Right? All of this is exact. I haven't done any approximations. All I did was factor out something and I rewrote it, right? Those are equal signs, correct? Now, the question is, what do we do with this? And this is where we do the expansion that I alluded to a little while ago. And we then remember, pull something from math. In math, you're told the following, that if you have 1 plus a small number, let me call it y so it's not confusing, raised to the nth power, such that it doesn't matter if this is plus or minus, the absolute value of that is much less than 1. In other words, if this quantity is much less than this number, then this approximates to 1, so you write the first number, plus this, n, so is this times the exponent, plus n minus 1, y squared over 2 factorial, plus, and then the pattern will be n minus 1, n minus 2, y cubed over 3 factorial, and you can see what the other terms are going to be. Like that. Now, because y is very small, right, then I am going to, I have, the first correction is this. Because if this is ridiculously small, I can set it equal to 0, and I'm just going to get 1. That's this term. But the first correction is going to be that one. It's the exponent times that thing. That's the first order correction. Because y is squared, because y is very small, and you square it, and then you cube it, and then you raise it to the 4th power. Any quantity that's very, very small, you cube it, raise it to the 4th, 5th, 6th power, they approximate to 0. So I am going to keep only the first term. I mean, the first 2 terms, the first correction. So this expression over here, just this quantity over here, approximates to 1 plus the exponent multiplied by the small quantity. So this will be 1 plus the exponent, which is minus 1/2, multiplied by the small quantity. Yes? And you do that for the other term as well. So this one. So notice that, therefore, now this is exact. If I substitute this by that, now this approximates to x over R1 times this quantity, right? which approximates to this, which is 1 minus, because that's a minus sign, right? X squared over 2r1 squared. That's what it approximates to. So, can I erase this now? Binomial expansion is what it's called.
Will we have to remember binomial expansion for the test?
What's that?
Will we have to remember binomial expansion for the test?
Forever. Not just for the test, forever. What is the root of the sine of x with respect to x?
Cosine?
You should remember that forever. Ever. Unless you're just taking this class for fun and you're going to be doing something else. Other than engineering, physics, physical chemistry. So therefore, what does this expression become? Well, I have I hat sigma over 2 epsilon naught multiplied by this term. Now, what does this term become? It becomes this, right? So it becomes x over r1 times 1 minus x squared over 2r1 squared, right? Right? And then I have to subtract the contribution from the other term. Minus, now this one, what will this become? It will be x over what? R2 times 1 minus x squared over 2 R2 squared, right? Now this is an approximation because there are other terms over here that I'm throwing away, right? From the expansion. Can I erase this, what's on the board over here? On this side? So, I guess a better answer to your question is that when I first learned about the binomial expansion, I learned it, applied it, forgot it. But then it came up in physics, and it came up again, and it came up again, in mechanics, in electromagnetism, in quantum mechanics, in optics. And I said, wow, that thing comes up a lot, I better know it. And so I've used it so much that I remember it. In other words, it may not seem like it's useful, but it comes up again and again and again and again. And so, oh, okay, so I gotta pay attention to it. So that I'll remember. So here, I'm gonna write equals now, because I'm just, so you just, I had sigma over 2 epsilon naught, and I'm just gonna multiply that through. So that'll be x over r1 minus x cubed over 2r1 cubed. And then this is minus x over r2. And then this minus with this minus will give me a plus x cubed over 2r2 cubed, right? And remember that x is very small compared to r, right? So, well, I'm going to throw away that one and that one. Yes? So I have that the electric field, therefore, is or approximately equal to I hat sigma over 2 epsilon naught. And I can write this as 1 over r1 minus 1 over r2. Or I can combine them, r2 minus r1 divided by r1 multiplied by r2, and then times x, right? Or if you like, you can write this as I hat sigma over 2 epsilon naught r2 minus r1, the difference between the radii, and then you multiply the two of them times x. This is the electric field, right? So where are we going with this problem? The question is this. Suppose you have this washer, and there's a hole, well, with a hole cut out over here, right? And you calculate the electric field somewhere on this axis. You know, it's a function of distance x. And that's this expression. What happens if you consider the value of that electric field very, very, very close to the center, but not at the center, right? And it looks like what they say in the problem is that now they take a point charge, like an electron or something, a point charge, right? That's negative. And the point charge is placed just a little bit off center. So which way is the electric field pointing? Suppose I'm considering a little point off center out of the board. At that point, which way is the electric field pointing?
Also out of the board.
Out of the board, right, away from the washer. Like, that would be like the x-axis, so the electric field is pointing that way, right? That's this electric field pointing. In this picture, I have this out of the board. But if I put a negative point charge over there, minus q, what will be the direction of the force on it? If the electric field is this way, you put a negative charge in there, the force on it is, well, the force is that. But the electric field is now this, right? Times that. Sigma 2 epsilon naught R2 minus R1 over R1 R2, if I remember. And then you have an x and well, I did the, well, I'll put the I hat over here, right? In fact, you can do this if you like. So which way is the force pointing? Inwards. So if I take this washer and it's charged uniformly with a charge per unit area sigma, it generates an electric field along the axis pointing away from the washer. If I put a negative point charge next to it and I hold it at a distance x that's small compared to this radii, and I let go, what's going to happen to that point charge? It's going to be pulled in. Now what happens when it goes past x equals 0 onto the other side? Then x becomes negative. Out of the washer is positive. On the other side of x equals 0, x is negative. And if x is negative, negative times negative is going to give me plus, so the force is going to be this way. So if the washer is here, you know, like that, right? So the electric field points that way and that way. If I put a point charge over here, that's negative, it's going to get attracted, right? It's going to get pulled. So it's going to go in like this, but then when it gets over here, it's going to get pulled this way. So what's going to happen is that the washer, the point charge is going to oscillate in, out, in, out, in, out, in, out. Now notice that the force, right? What do you notice about this force? How does it depend with the distance away from the, in fact, how about I do this? Maybe I'll write it like this, so this looks more familiar. Minus Q sigma 2 epsilon naught R2 minus R1 over R1 R2 times X. Does this look like something you saw before? In physics 185? So all of these are just numbers, right? Depending on the size of the washer, the inner radius, the outer radius, the charge of the point charge that I placed next to it, the charge per unit area on it, that's a number. What if I call all of this, all of this is just a number, right? All of this is just like some number, some constant. Suppose I call it K. This is F equals minus KX. Maybe if I write it like this, it'll be more familiar. That's the force exerted by a spring, which exerts a restoring force, right? You have a spring, let's say x equals 0 is over here. I attach a mass to it, I pull it, the spring pulls this way. But as soon as the mass goes past the equilibrium position onto the other side, the spring pushes the other way. So the thing is made to oscillate back and forth like this about the x equals 0 position. And that's what's going to happen to this charge when released from rest, a little bit off axis, right? You let go, it's going to go in, up, in, up. You need this hole over there. Because if you had a disk over here, the charge would go and hit the disk, right? But if you cut the hole, it'll go in, out, in, out, in, out, in, out. So if you look at your notes for simple harmonic motion, right? The angular frequency of oscillation is 2 pi f. And the angular frequency, omega, is, well, the angular frequency in radians per second is 2 pi times the frequency in hertz. So for a spring mass system, right, this is equal to the square root of k over m, where k is the spring constant. So this is effectively, this number over here is the spring constant. So if you set this equal to 2 pi f, the frequency of oscillation, how many oscillations it's going to make in 1 second, will be 1 over 2 pi times the square root of the spring constant divided by the mass of the charged particle, where the spring constant is given by this. So the result is that f, the frequency of oscillation, will be 1 over 2 pi times the square root of, I'll just put the m over here so I don't forget it, and then I have to put this constant, q sigma r2 minus r1 over 2 epsilon naught, and I hope I don't forget anything. If you evaluate this, this is going to be a frequency in hertz. And that'll tell you how many oscillations this thing is going to make in 1 second.
This only works if the point charge is negative.
Yes, because if the point charge is positive, the force is going to be this way. It's never going to come back. It will not oscillate. It'll just leave. It'll be like that other problem that we just did, where we had the 2 point charges that were positive, and you release this one, a positive charge somewhere over here. It's just going to go up the y-axis, and it's not going to come back. Exactly. But this result, for this frequency of oscillation, right, you can only use these expressions, right, if the force is proportional to the displacement from the equilibrium position. Which it is, if you consider locations that are very close to it. If you release the point charge somewhere over here, like, some considerable distance over here, it's still going to go in and it'll go to the other side and come back and oscillate, right? But the frequency of oscillation is going to be different. But we can at least calculate it if it starts, somewhere. The point is that this problem, there are many parts to it. One is, what is the total charge of this thing if you know the charge per unit area? That's one thing, right? That's one part. Another thing is, what's the electric field generated somewhere on the axis? It's just a problem of the disk that we did with a hole cut out. You just, instead of integrating from 0, r equals 0 to the radius, you integrate from r1 to r2. Right? And now you have this expression for the electric field. And now you're just adding something to it, right? Well, what would the electric field be if you're very, very close, if x is very small compared to the radius of this washer? Well, it'll be given by this, right? It'll be given by actually this. And then you notice that the electric field is proportional to the distance away from the center. So if you put a point charge over there that's negative, it'll be pulled in, and then pull, it'll oscillate with simple harmonic motion. But then you ask, what frequency? Then you pull this, and you can figure out with what frequency the thing is going to vibrate, oscillate. Questions? Something that I didn't emphasize, and the other thing about this problem that's cute, is the fact that you need to pull something from math. I mean, you have to construct the integral, you have to solve the integral turns out to be trivial, right? But at some point, it's like, what do I do next? And then, this step that I did over here slowly, right? It's one that you end up doing a lot. So, look at it, get comfortable with it, you do it again and again and again. See, one fundamental difference between electric fields and electric potentials is the following. If I consider a ring, so that would be like the washer where, you know, the two radii are very, very close to one another. Let's just call it a ring of radius, you can call it R or A. I'll call it R then. What's this ring? And suppose that it is uniformly charged with Q. So Q is the total charge in this ring. So it's a ring. Right? With a big hole cut out in the center, right? A ring. Not a disc, not a quarter, penny, not a coin, but a ring, right? Now, if I ask you, what is the electric field produced by this charge at the center? What would you say?
0.
Why?
Because it cancels out. The field cancels itself at the infinitesimal charges around it.
Exactly. So if I consider the Q over here, it's going to generate an electric field pointing that way, right? But if I go to the other side and I consider the same amount of dq, it's going to produce an electric field this way, and they'll cancel, right? So that's correct. Now, what if I ask you instead, what is the electric potential there? V at the center, right? Right there. What's the electric potential there? Actually, you could do this in your head.
Zero.
Why 0?
Or wait, is it undefined?
What's that?
Is it undefined? Or is it 0?
No. Why would it be undefined?
Because isn't electric potential KQ over R? So wouldn't it be in it?
But what is R?
The radius?
In that expression that you said, KQ over R, what is R? It's the distance from the charge
Oh.
to the point.
I see. Yeah.
But if you want to calculate the electric potential at the location of the charge, right, for that point charge, then you divide by 0. But in this case, the charge is not at the center.
Right. The charge is the ring.
The charge is in the ring, so that R that you mentioned is from the charge in the ring to the center, which is the radius of this ring. So what is the electric potential at the center? Well, what would it be if I due to this charge? What would that potential be? What is the electric potential dV at the center? This is the easiest problem in the world, having to do with electric potential with charge distributed. Why do I say that? So, if you don't see it, it's because you're missing the point. First of all, right? I'm glad that nobody said it cancels out. The cancellation comment was good because I was talking about electric fields, which is a vector. This is electric potential. So there's no like this way and that way canceling out. None of that. So I didn't hear that, so that's good, right? So, but what would be the electric potential there due to this little bit of charge? Just think of this as a point charge. What would it be? K dq over the radius of it, which is A, right? Or I call it capital R, right? And that would be this R, right? Because that's the distance from the Q to the field point. Now, how do I get the potential there due to all the charge?
Integrate from 0 to 2.
Then I gotta find the potential there due to the next little bit of charge and the next one and the next one and the next one and the next one. Can you see that every little bit of charge is at the same distance away? So it's like adding this, you know, to this, right? Blah, 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 blah. But that's the integral. But K and R are constants. So it's just, and what is this? This is just the sum of all the dq's. This is K, Q over R. All the charge is at the same distance away from the field of point of interest. So it's just K times all the charge divided by the distance from the charge to the point, K Q over R. Where R now is, this is not the electric potential generated by a point charge capital Q. No, this is the electric potential generated by charge distributed over a ring. And it doesn't cancel out because you don't say that this cancels this and this cancels that, because potential is not a vector quantity, it's a scalar quantity. So it's just the sum, the sum, the sum, the sum, the sum, the sum, the sum. Yes? What if you had a problem like this? So, noticing that all the charge is at the same distance away from this, it's like k dq over r. Well, r is the same. K is a constant, so it should be just k over r times the total charge when you do the sum, just kq over r. What if we have a problem like this? So you have a ring, that's supposed to be a ring, a radius r. And suppose that the charge over here, I think I can do better than that. Suppose this charge is Q plus, and this charge is minus the same amount. What's the potential at the center? 0. Now you'll have cancellation, but not because of the vectors, but because what will be the electric potential here, due to the red charge?
KQ over R.
Okay. Do I want that Q or half of it? What does this represent over here? I'm so glad I'm asking these questions. So what should I write over here, KQ over R or K 1/2 of Q over R? It's a trick question. Yeah. I just want the charge this is the charge that's going to contribute to that potential, right? And that's Q. But what is the electric potential over there due to this charge? This one, the one that's over here in purple.
Negative
Is
KQ.
K times that charge, because all of that is at the same distance. K times minus Q over R. And the total potential is going to be the sum of those two. I don't have to worry about cosines and sines of thetas of angles because it's not a vector quantity. So it's just this plus this, which is going to give me 0. So, this question over here, a lot of people say, oh, if the electric field is 0, that means that the potential has to be 0. No. That's like asking, what is the acceleration at the highest point? Oh, it stops, so the acceleration is 0. No, the velocity is 0. That doesn't mean that the acceleration is 0. Just because one thing is 0 doesn't mean the other one is also 0. In the case of velocity and acceleration, if it stops and stays there, so that the velocity doesn't change anymore, then the acceleration is 0.